Welcome to this talk. I'm going to talk about our paper that's called Amortized Circuit Complexity, Formal Complexity Measures, and Catalytic Algorithms. At a high level, our paper is about a class of problems that's called direct sum problems. And these problems are about the following kind of question. Namely, is the fastest way to solve n instances of some problem P just to run the fastest algorithm for a single instance n times? Or is economy of scale possible? So mathematically, we can maybe imagine solving a problem P n times, looking at its cost and dividing it by n, and then trying to understand what happens if we let n go to infinity. So this is some sort of amortized cost on the left-hand side. And what we would like to know is whether this amortized cost is equal to the one-shot cost. So the cost of computing P a single time. And these direct sum problems, they appear everywhere in complexity theory and beyond. Here are some examples. So in information theory, they appear in Shannon source coding and Sleeping Wolf. In communication complexity, there is an important example related to this information equals amortized communication paper of Braverman and Rao. And there's parallel repetition and so on. And sometimes these direct sum problems, they're actually less obviously direct sum problems. And an example of this is matrix multiplication. So here, the problem is to understand what is the smallest real number omega, such that two n by n matrices can be multiplied in n to the power omega arithmetic operations. And it's known that this number omega, this image multiplication exponent, is between 2 and 2.37286. Following a long line of work. And this can be seen as a direct sum problem in the following ways. If we multiply two matrices A and B, then this is, of course, we can think of this, of course, as computing n matrix vector products. And what we're trying to do here is to do this better in like an amortized time. And here's another way of thinking of this as a direct sum problem, namely this 2 to the power omega is exactly the asymptotic tensor rank of some special tensor T. And here, this is not very important, but it's only for the backstory here. This asymptotic tensor rank is defined as of a tensor A is defined as the rank of the product of m copies of A to the power 1 over m, where we let m go to infinity. So you see that this is also some sort of amortized parameter, this asymptotic rank. Now, I want to say something about Strassen duality. So Strassen introduced a general duality theorem to capture this asymptotic rank and other asymptotic or amortized parameters. And this duality roughly goes as follows. So Strassen defines a set X of all functions mu from tensors to the real numbers, such that mu is a multiplicative and additive function. Mu is monotone under some natural notion of reduction on tensors, and mu is normalized to n on diagonal tensors of size n by n by n. And Strassen proves that this asymptotic rank that I just talked about, which also characterizes the image multiplication exponent, can be written as a maximization over all mu, over all these mu here, applied to T. And this is a very powerful theorem with lots of implications. It's also very general. It can actually, its general version can be applied in lots of other settings, such as Shannon capacity, sunflowers, and cap sets. So this is all interesting. It is all in the algebraic setting. Now I want to talk about the Boolean setting. So in the Boolean setting, there is a notion called formal complexity measures, which is very important, and it arises as follows. So a Boolean formula is a tree-like Boolean circuit that uses these and, or, and not gates in the following tree-like fashion. And we define capital F as the formula size, so the size of the smallest Boolean formula computing F, the Boolean function F. And a formal complexity measure is a map mu from Boolean functions to the real numbers, such that mu is monotone with respect to and or in the following way. So mu of the logical end of F and G is at most the sum of mu of F and mu of G. And similarly, mu of F or G is at most mu of F plus mu of G. And also mu is normalized on literals, so mu of any variable or any negated variable is at most 1. And it's not very hard to prove that for any Boolean function F, the formula size of F equals the maximum over all these formal complexity measures mu applied to F. So what we're seeing here is that on the one hand, we have this Strassen duality that I explained first, where we write this asymptotic rank in terms of as a maximization over these special functions mu applied to our tensor. And on the other hand, we have this theorem for Boolean functions, which says that the formula size of a Boolean function equals the maximization over special functions mu again, which have these monotonicity and normalization properties. And maybe these look very similar to you. I think they do. And is this a coincidence? And the answer is no, and that's what our paper tries to explore. And to explain this, I am going to talk now about a notion that we introduced, which is amortized circuit complexity. We introduced it in a very general fashion. So for any, we pick any finite gate set, G, which is complete so that it can compute all Boolean functions. And this gate set can really be very general. So we allow every gate to have like multiple inputs, multiple outputs. And we allow you to specify different costs per gate that you use to measure the cost of your circuit. Okay, now we define, given a collection of Boolean functions, F1 up to Fn, we define the circuit cost with this gate set just as the minimum cost of any G circuit computing all these functions at the same time. Yeah. And I will give some examples to clarify how general this is and make it more explicit. So I want to talk about formulas, comparator circuits, and branching programs. So let's do that. Here we have the setting of formulas. Here the gate set has an AND gate and an OR gate, and it has a gate that produces a variable and a negated variable. And what I'd like to do is give the AND and OR gate cost 0 and the literals cost 1. This will become clear in a moment. So now with this gate set, we're allowed to combine these gates in the usual way. So I can put these variables here and then apply these AND and OR gates to them. I can also do this. I can have like a collection of these trees, so like a forest. And in this way, we are computing these two functions, f and g. And like I said, we assign cost 1 to the variable. So this is measuring the cost of the cost here is the number of leaves that we use in our formula. So here we see that the cost is 6, or at most 6. A comparator circuit is the second example. Here the gate set is smaller, so we have only we have this comparator gate which takes 2 Boolean functions and simultaneously computes the AND and the OR of the Boolean functions, and we still have these gates that will produce for us these literals. And here's a nice way to draw these comparator circuits. We start with a bunch of literals on the left, and then we start applying these comparator gates like this. So here we have 3 comparator gates that are applied, and on the right-hand side we compute these functions. And here the cost is the number of like these horizontal wires in the circuit. So in this example, it's 3. And finally, there's the branching programs, which is maybe the most complicated. Here we have a query gate, which takes f and then outputs f and xi, and also f and the negation of xi. It has an OR gate, and it has a gate which produces the constant function 1. And here the cost will be the number of queries that we need to make to literal, to like variables to compute f. And we can draw this as follows. So we start on the left with a constant 1, and then we apply a single query gate over here. Here's another query gate. Here's another query gate. And here you see that we have an OR gate. And yeah, one way to interpret these kind of circuits is that we compute f1, for example, as follows: f1 equals 1 if and only if there is a path from some source node. In this case, there's only one source node, but it could be multiple, from some source node to the sink node that's labeled f1. So that's the way this kind of circuit computes Boolean functions. And yeah, here the cost of this circuit over here is 3. There are 3 query gates. All right. Now, so we have seen some examples of these kind of gate sets. Here's our first result. I'm going to talk about 3 results. Here's the first one. It's a duality theorem. And to explain this duality theorem, I will first define this CG twiddle of the Boolean function f, which is the amortized G circuit complexity, which is defined as the cost of computing n copies of the function f divided by m, where we let m go to infinity. And to explain the duality to you, I define a G complexity measure as a function mu from Boolean functions to the reals that is G gate monotone. So this means that if there is a G gate that maps this collection of Boolean functions f1 up to fn to g1 up to gm, and the cost of this gate is c, then we want this function mu to satisfy this inequality. So mu of f1, the sum of the mu of the fi's plus c has to be at least the sum of the mu applied to the gi's. Okay. Then we prove that the amortized G circuit complexity of f equals the maximization over all these G complexity measures applied to the Boolean function f. And yeah, to prove this, we use LP duality. Let me talk briefly about an application of this to submodular measures and comparator circuits. Submodular measures have been introduced by Robere. They're defined as follows: they're these functions on Boolean functions to the reals that have these 2 properties: mu of f and g plus mu of f or g is at most the sum of mu of f and mu of g. And these mu's are normalized in this fashion. And Robere showed that for every such mu, mu applied to f when f is a Boolean function on n variables is at most big O of n. Potassian later made a more concrete, explicit construction for this. What we can do is we can apply our duality theorem to the theorem of Robere, because these submodular measures turn out, if you look at them, to be exactly the functions mu that are G monotone for the comparator circuits. So if we apply our duality theorem, we obtain that the amortized comparator circuit size of any Boolean function f on n variables is at most big O of n. Okay. Now, our second result is about something that we call catalytic circuits that we introduce. Let me explain it to you in the language of comparator circuits. A catalytic comparator circuit is a comparator circuit that, besides literals, takes also Boolean functions as input, which it in the end of the computation reproduces as outputs. So it can use these HIs, these Boolean functions. It gets them for free, but it has to reproduce them at the end. So we can think of them as catalysts in the computation. And the theorem that we prove is that if we denote by CG-cat, the catalytic comparator circuit size of F, so that's like the smallest circuit that computes a single copy of F, but it's allowed to use arbitrary catalysts in the computation. We prove that this number is at most the comparator circuit size. That's not surprising. It's at least the amortized comparator circuit size. And we prove that this equals the optimal integral solution to some LP. So we can really characterize this catalytic complexity notion. All right, let me talk about our third result, which is about catalytic space. So this notion of a catalytic Turing machine was introduced by Berman et al. In 2014. Roughly speaking, what it does is, besides the standard input tape and work tape of the Turing machine, there is a special catalytic tape, which can be super long tape, that starts with some arbitrary content alpha, and we can use it however we like, but it must be restored to alpha at the end of the computation. Okay, and they prove that TC1 is contained in catalytic log space. So where the work tape has log space. And now we have seen the word catalytic twice already in two ways. So first I talked about catalytic circuits, and now I'm talking about catalytic space. So maybe let's take a second to compare them. In the first, so there are different notions. In the first, we say that there exists a catalyst that helps computation. That's what a catalytic circuit does, and the circuit can depend on the catalyst. In the second, we want that for any content of the catalytic tape, the Turing machine must work, and the tape must be restored. And in particular, the Turing machine cannot depend on the content of the catalytic tape. Okay, so there is a clear difference between these two. However, we can use our techniques to still say something about the second. But before I go there, at first talk, I have to move to the non-uniform setting, so non-uniform catalytic space. This this non-uniform analog was introduced by Gerard, Couchke, and McKenzie. They define an M catalytic branching program for a Boolean function as a branching program with a special structure. So it has M start nodes, and it has M accept nodes and M reject nodes here on the right. And on every input X, we the query gates that are in this branching program, they evaluate in a way that we get paths from a start node to either an accept node or a reject node. And they are paired in a very special way. So if f of x equals 1, then we have then we have paths from Si to Ai. And if it's 0, then we have paths from Si to Ri. Okay, but they're always paired, these S's and A's and R's. That's very special about these catalytic branching programs. So GK and M, they asked, when is the M catalytic branching program size divided by M smaller than the branching program size? And protection showed that every function f has an M catalytic branching program size of size M times N, when M is like this doubly exponential function. And he asked, can we improve this? And we showed that indeed we can improve this. Namely, we showed that for every function f, there is an M catalytic branching program of size Mn, when M is 2 to the power n choose at most the f2 degree of f. And the way we obtain this theorem is by translating a new upper bound that we proved using our duality theorem, and by heavily exploiting this symmetry group of Boolean functions. So even though this notion of catalytic space is very different from catalytic algorithms, we can still use our result to get this construction. All right, thanks.